Hi, I worked with Stephen Moreland this summer to explore opportunities for introducing formal methods into the Android ecosystem. So I'm going to first introduce what that even means, and then show two applications that we looked at, and finally give a perspective on what future efforts could look like in light of what we learned. So for background on what formal verification or formal methods even is, I'm going to focus on the first two of these questions. So I think two quotes really get at the why. This first from Dijkstra is getting at the fact that unit testing can't give us confidence in the correctness of programs with infinitely many behaviors. And it's not that there's something fundamentally difficult about reasoning about infinities, like for every integer I plus 1 is greater than I, but really the arguments that justify claims like those must go beyond just checking that such and such function yields such and such value. So there's certainly some added value in the expressive power of formal methods insofar as they give you a language in which you can assert and check statements such as that for all possible inputs of a program. But testing at the end of the day is just something that you can run and get a yes or no for a given program, so can we do better? And I think the second quote gets at how we can, elucidating the assumptions upon which formal correctness depends. So suppose we have code that we want to make sure is correct, which here would mean it has some formal property P. So through trial and error, you could eventually see that no, P doesn't hold of my program unless I have to assume this about the input, and oh, I have to assume that about the environment because I'm doing I/O, and I have to modify this line here in order to finally get P to hold. And so the conclusion of this is that we're not investing this effort into formal methods just to get a yes or no answer for a particular program, but rather it's a tool that is guiding the development of our software. So one way of showing the value of formal methods is by making design itself formal. So this is design as code as opposed to purely prose design docs. In software, engineering rightly places a strong emphasis on the design phase. This is the cheapest area to find and fix errors with a product. So I'm going to quickly walk through this example from a tutorial of a formal verification software called Alloy. I hope it can illustrate these points even without you understanding the syntax or how Alloy works. So just imagine we're a software team. We're working on some application that involves a file system, so we're going to model that file system. Firstly, we need to name things that exist and the relationships between them. So for example, this first line, it's saying that there exists something called an FS object. Each has a parent, which is either 0 or 1 directories, whatever those are. So you can think of parent as some nullable foreign key, and really just declaring signatures like this is specifying a schema of sort. So we can go beyond that, just specifying the schema, and actually have this language for asserting properties, which we're going to assume hold of objects. So in Alloy, these are called facts, and the comments above the three facts I've highlighted really show what kinds of models that we're actually excluding in virtue of that fact. So there might be, if we look at the last one, there might be disconnected file systems, which are syntactically look like a file system given the signature, but we just want to exclude those from our observation. So in addition to letting us assume things, formal verification allows us to check and prove assertions that follow from our assumptions. So here are three examples of properties that hold of file systems as defined on the left-hand side. So now we'll come back to the problem of what's wrong with designs not being code. In the first hand, you could imagine if we throw away everything that is not a comment, we would get something that might be ambiguous. There are certain words like unique or connected, which are up to interpretation. So these kinds of natural language issues can be resolved when working with a formal model. But more interestingly, we can eliminate contradictions in design with the style. And contradictions in design sound kind of absurd when you think of an engineer developing a design in isolation. And this is really a problem that comes with scale. So imagine we're in black box number 3. We're assuming that we're writing some application for a file system, and we need to assume that it's acyclic for our algorithm to terminate. Some other team in black box 2 is implementing the file system, and they're not really conscious of what we're trying to do, so they actually don't include the required fact to prove acyclicity. And a tool like Alloy can show that team 2 needs to make some changes in order for our expectations to match. And maybe that change causes problems downstream for team 1. So it's a complicated problem, but we're essentially using this formal model as a static type checker to make sure all the teams' work are fitting into a coherent whole. And to conclude with a not toy example, we have specifications in Android that have a lot of rich logical information, and perhaps a figure like this is not the most simple way of communicating this information to a new engineer who's interacting with the build system. And certainly this figure will not enforce mechanically that any designs that that other engineer who's reading this is going to have to adhere to. So that sort of gets at the why of formal methods. And now to talk about what they aren't just one thing. It's really multiple things that we could arrange along a spectrum like this. Starting at the left, we have the Boolean satisfiability problem. We're essentially verifying claims made in the language of propositional logic, where you have Boolean variables combined with connectives like or and not and. And this is really an easy problem, despite being NP complete, in virtue of being decidable. And we're really just happy to have that here. But we often want to say more expressive things. We want to say, for all x that satisfies some property p, there exists a q. And this level of expressivity is the domain of first order logic. SMT is really the workhorse at this level of theory, and the solvers can be really clever and more or less completely automatic. But we also want to say more expressive things. So I already gave an example in this category from Alloy. I consider this category of tools which are built on top of SMT, but they have extra flavors of reasoning. They're still automatic, but it's very possible for you to specify some kind of proof that you want to give that it's not able to give. So it fails to prove something one way or another. Or in the case of Alloy, maybe it gives you a proof which is certain, but it's only certain up to file systems of a certain size. So this last category is really the most expressive languages of dependent type theory and higher order logic. It's basically possible to say anything you would want to say. And this allows us to fully talk about programming languages or advanced mathematics. What we're losing is the ability to automatically generate proofs. So I'm going to focus on one of these tools in this last column. For most of the talk, I've bolded it here called Lean. And to briefly summarize how these tools work, I think it helps to view them more or less just as programming languages. But these are programming languages with really interesting types. And in a very rigorous way, the data types correspond to logical propositions, and values of those types correspond to proofs of that proposition. And this sounds bizarre the first time you hear it because you think, oh, I have a data type integer or string. What proposition is the number 7 proving? But to see really this connection between logic and types, imagine that firstly that you have a function type, which makes sense. But really, what is that doing in this world? It's saying, if you give me a proof of A, I'm going to give you a proof of B, which is more or less implication. And if you have a product type, which is a pair, that is saying I have a proof of A and a proof of B. So now we have logical and. So if I were to tell you, give me a function which takes a pair AB and returns me a pair BA, can you implement that function? Well, that's just swap, and you should be able to implement that. But what you've inadvertently done is proven that and, logical and, is symmetric. And conversely, if I were to not tell you anything about A and B and say, implement a function A to B, then you would never be able to implement that because you have no idea how to construct a B. And that's good that you can't implement that function because that would imply that there is a proof from an arbitrary A to an arbitrary B. So now I hope you can see how it works to prove things in Lean at a high level. You essentially start by writing a data type which corresponds to some function. It's corresponding to some fact that you're trying to prove. And then you just have to implement the function. And if you can do so in a way that type checks, that means that you have a proof of that proposition. So what sorts of programs could we write in such a language that would be value to actual engineers instead of just academics? So the context for this upcoming problem of structure packing is the fact that Android supports 32 and 64-bit binaries. And this can be a problem in fast message queue and applications which have interfaces between processes that might be from different bitnesses. The important difference between 64 and 32-bit for our case is in the top right-hand corner, where it turns out that the alignment of the int64 type is different. And alignment is significant because suppose you have a structure and you have all these different fields. You can't just have these all in contiguous pieces of memory. Each data type must be aligned at a certain point in memory. So this means that you have to insert padding in between certain elements of your structure. So the fact that int64 has this larger alignment would mean that maybe int64 structures have more padding, and so they might have a different size even. But the interesting case is where we have the one single struct that we pad it in both 64 and 32-bit, and yet it does have the exact same size. So can we assume from this that it's actually the same padded struct, so that the pads, the memory layout, is exactly the same? And it's very hard to think of an example where the padding would just be shifted in a different place. But this ends up posing a problem because we could very easily do a size check and get a lot more information out of it, as opposed to having to actually implement code that verifies that the memory layouts are the exact same. So we could do this thing which is complicated in the code, or we could actually prove that our assumption that size equal implies that the padded layout is equal. So we want to prove this fact in Lean. So note that I say a model, a formal model rather than the formal model. We've been through a lot of iterations on this, and we've had varying degrees of success. So first, we declare a primitive type, which would be int 8, 32, 64, and we're going to declare this as an inductive type. And this corresponds to something like a sum type or an enum, if you're familiar with that. And really, it's just saying these are the possible ways, the only ways you could construct a prim type. And it's similar for defining a structure, except now we see that these constructors can also take arguments. So we have one constructor which starts a structure, we have another one which adds one of the primitive types, and then we have another one which adds an entire nested structure. So we next need a type to represent the layout of bytes in a structure that's been padded. So first we need to, one way we could do this is to just have something that's very similar to struct, but with every constructor we add this argument, which is a number between 0 and 8, which are all the possible paddings. So this has some advantages insofar as we're enforcing in the type that there is exactly one padding between each element. And so on that note, we have at the bottom the type signature of what it means to pad a structure. We take an arbitrary bitness, which is 32 or 64. We take an arbitrary struct, and we're going to produce a padded struct. The most interesting thing here is the data type, which corresponds to the proof that we care about. So this is a function type which takes in an arbitrary structure, i.e. it holds for all structures. And it takes a proof that the resulting size of padding with 32 and 64-bit is equal. And what we have to construct is a proof that the actual padded structs are equal. So if we can implement this function, then we have proven the theorem of interest and we can rest easy. So just briefly, I'm going to show a taste of what it looks like to implement the pad function in a language like Lean. There's nothing bizarre here. There's just a lot of cases to handle, modular arithmetic and recursion, but more or less this is programming in a straightforward functional style. Also, here's a taste of what proofs look like in Lean's tactic language. So there's, in this point in the proof, we've done a lot of enfolding definitions, we split on cases, we prove things via induction. So given all this work, we need to make a practical decision in Android systems, which is, do we just implement the checks wherever we were making this assumption? And while this may take perhaps 10 man-hours of upfront cost, there's also a lot of hidden costs of this approach insofar as we're introducing complexity into the code base, we now have new surface area for bugs, and we're adding to the build time in disk space. The alternative that I worked on was proving that our assumption is valid. So if we can do this, we now have complexity, but it lives outside of the code base. Now, it turns out that this assumption may be invalid, in which case we then have to implement the checks afterwards. Note that a model checker could also be used to show that this assumption is valid, but it would only show its validity up to a certain size. So you would always have this lingering doubt. So that was a sort of mini project application of formal methods, and now I want to show the primary problem that my internship was geared towards. So to get back to this figure, the details of which are deprecated, but really at a high level, what it's saying is that Android build system has to build C++ libraries of many different flavors in a high level. So what do we call those flavors? How exactly do we partition the space of all possible libraries into overlapping flavors? And what expectations we hold for each flavor? These all end up being decisions that are not centralized in any one location. There's enough cohesion between teams to avoid chaos, but Stevens documented a list of bugs that have arisen due to mismatched expectations between what these categories actually mean. So this sounds like a good application for a formal model like we discussed in the beginning. So we start that by declaring a schema for what exists. So consider this example soon configuration file, which would be the raw input from a user. They're basically specifying these libraries, which are no more than just these structures in Lean, just a simple data structure. So the details of that are not really important. I want to show that the flavors of different libraries, we're going to give them a name of library class, and we're going to, we're going to specify upfront what are these actual library classes. So we're going to fix that in our model. So these classes are really just a way of thinking about libraries where within a given class, we expect uniform behavior in some sense. For lots of attributes. So we're going to focus on one particular attribute, which is something called variants. So variants are like different environments that libraries get compiled in during the build. And any given library could have some subset of these variants. And what we want to assume is that, or what we provide by construction is that each library class has some variants associated with it. So we need some idealized specification in our high-level model of how to assign library classes to a given library. So we implement this function, which takes in a library. It gives some set of library classes as a result. And then we can complete this pipeline by essentially, we first compute the library classes, and then we just union all over the associated variants for each library class. So the fact that this is so elegant and clean to specify is one of the advantages of defining the concept of a library class. And note that none of this code exists in the code base anywhere. This is all stuff that currently lives in the heads of engineers. So we could, at this high level of modeling, we could already do some of the techniques that we've discussed, but there really aren't many properties of interest to verify of the model itself as we have here. So the focus I want to make is on a methodology for verifying soon code itself, not just the high level model. And to do this, we need to first consider how the build process works. It's operating on this graph of libraries that are connected by their dependencies. And what we ultimately do is we start with a config file and we have this set of mutators. Each mutator is essentially a pass of the build system which modifies this graph in some way. So what can we say about each of these mutators? They each definitely have some source code associated with them that performs what they're supposed to do. But more importantly, they all have something that they're supposed to do. This is something that we could specify as a high-level property in the language of our high-level model. But we need to connect that specification to the code itself. So what would that connection look like? Consider the fact that this particular mutator we're looking at, which is called image mutator, its job is to assign variants. And therefore, the role that this code plays is precisely identical to this function that we defined here, which assigns variants to a given library. So the specification really writes itself. Basically, we want to say, for every input, we assume that image mutator must terminate and that it terminates with the exact same value as our high-level function also gives. And I would also want to note that this process of formalizing mutators really lends itself to a gradual process, and mutators can in piecemeal be formalized without breaking anything in production. So I'm now talking about verifying code itself, and that's completely new. I haven't talked about that yet. So what are some complications that come along with doing this? Firstly, we need to say what it means to prove things about a program. And I've shown inductive types are things we can prove things about. Well, we can represent programs as an inductive type. We have these primitive operations, which are constructors, and then one of these constructors is called sequence. And it's going to combine two sub-programs into a larger program. Now we might ask, like, what is this modeling process? How does it depend on the actual language we're trying to model? And it definitely depends on it. We have to implement the rules for evaluating expressions and a rule for saying how do we update the environment given a given primitive operation. And then we also need a model of the environment itself, which in our case will be a store and a heap. And lastly, we're proving things about this inductive type. What's the connection between that and the source code? In what way are we licensed to say that we're actually verifying the source code? So there are three general strategies for doing this. The first being parsing actual source code into the formal model. Another technique called program extraction, which just takes a formal model and generates code in a very pure and rigorous way, though sometimes this has problems with performance. So another simple way of generating source code from the formal model is to write an ad hoc function which pretty prints your formal model into the language that you care about. So this gives you a lot more control over what does the final code actually look like and its performance characteristics. But you have to trust that you implemented this pretty printer correctly. So we actually opted for this third strategy this summer. So in the interest of time, I'm going to now breeze by some of the content that really makes up the bulk of the work this summer, which was to build up an infrastructure for modeling Go code within Lean. So the topics of Hoare logic and separation logic are really crucial to how one does this, and they're essentially theories of how to deductively prove things about programs in a scalable way. And separation logic is really just an extension of Hoare logic, which models memory and mutation. So these are each broad categories that have many flavors that had to be specialized to talk about soon Golang code. So we started with Hoare logic and eventually found that the types of programs we wanted to express would require separation logic. So that's what I'll be showing. And firstly, we need to modify data types in Go themselves. These are just simple inductive types. And we also want to model values of those types. So this is a type that's parameterized by a Go type called a type decal. And then we have sort of as the first argument, really the Lean representation of that value. We also model the store as a finite map from strings to values and heap as a finite map from integer to value. And a big component of this model is the programming language itself. So this is that inductive type of programs that I mentioned. So we draw a lot of primitives from conventional separation logic papers, but then we explored some other Go-specific structures, such as initializing an instance of some struct or calling a method of a struct. So this is going beyond sort of the vanilla separation logic that you see in papers. So we implemented method calls, firstly by defining signatures for methods. We also have to have a type representing the struct declaration itself, which has the fields and the methods, and then some data structure which maps the names of all these structures to their declarations. So that decals is essentially the static information about all the types that we've constructed. And really, it's now part of our program context. So usually the context is just a store and a heap, but now our context is store, heap, and decals. So lastly, we have this data type, which I had briefly alluded to, which says, given some context, some programming environment, and given some primitive operation, how do we conclude something about the resulting environment? So this is also an inductive type. And really, this is the assembly code for the assembly language for separation logic proofs. This is really defining the semantics of our logic and saying that this is how you prove that something follows from a given program. So all proofs will eventually reduce to elements constructed by this constructor, but really you need much higher level infrastructure to do things in a useful way. So instead of focusing on what those higher level abstractions are, I want to talk about an example. We are debugging our infrastructure while developing this with an example with a linked list, which has a method which checks whether the linked list is cyclic. So the strategy which we implemented was kind of roundabout because we didn't have arrays or maps. So what we said was this cyclic function is going to take two arguments. First, it's going to take a Boolean, which says, I'm calling this function for the very first time. And then it has a value which stores a pointer to the head of the linked list. So the first time you call this function, you ignore the second value and you actually store as the head of the list the current pointer that you're pointing to. And then you recursively go through, you follow this linked list, and if you ever see the head ever again, then you're going to say it's cyclic, and otherwise you're going to say it's not cyclic. And so we can pretty print this to the code on the right, and this is like, you can see on the left-hand side what this program also looks like in Lean, and that is, it's not super easy. It's not as easy as writing Go code itself, but because you can declare your own notation, it can be somewhat straightforward to write programs in Lean that look like certain Go programs. So the next step in this example then would be to prove that this program is correct. So we can define a pure Lean function which captures cyclicity and then prove that our function agrees with it on all inputs. Of course, we started that but realized that this would never work because our program actually isn't correct. We'd never detect one of these interesting cycles of that don't include the head of the list. So this is another cautionary tale in verification. But rather than focus on that, I want to talk about the basic workflow applied to the mutators themselves. So we have basically this code that already exists in Soong, and it's pretty easy to define in Lean a program that has the same semantic value. So this is just a straightforward translation of the program in Go, which then will get pretty printed into Go. But now it's worth showing concretely what the definition of the theorem we want to prove is, because this data type is really the most interesting part. The actual proof is just a drudgery of trying to implement a term of this type. So this type is the interesting thing. So firstly, we see that we're proving something for every possible library, and we parameterize the pre and post conditions of our program, image mutator begin, which is IMB. We're going to parameterize those conditions by that library. So what's the precondition given a particular library? So we're going to assume that this mutator, which is just a method called on the library, there's no arguments, so it's just the starting environment is completely specified by the object that is calling the method. So what we can do is essentially using some notation say that the pointer of the callee is going to essentially what that library is. So we have a simple function which converts a Lean value in the high level model into a Go value. And we're just saying that that is what is calling this function. The post condition is a little scary looking, but really a lot of it is just noise, which is making sure that all the pointers involved are not null pointers, and that we can, when we unpack all of those pointers, we get to some value, and we're basically checking that the value from the program is equal to the value from our library to variant function that we implemented at the high level. So that was a really whirlwind tour of the type of stuff that was going on this summer, and now I want to talk about what future directions we want to take. So reflecting on my time here, it's clear that there's lots of challenges that stand in the way of getting value from this fourth category of formal methods. There's a huge amount of work in setting up a usable separation logic framework, and that's like before you even get into the issues of proving things, which is also very difficult and really the real bottleneck. So the fact that you can't easily automate your proofs is one issue, but also the literature in this field is really focused on maybe more vanilla cases that don't specialize. It's really kept general, whereas we wanted to actually have a concrete, we had a concrete goal in mind of what we wanted to model. And so whenever we tried to extend the literature, we would end up into having to prove a lot of things on our own and sort of go in the dark. So those were some challenges, but there's also a lot of advantages. There was so much help from online communities like Zulip, where these languages have a lot of passionate people working on it, and they can be very helpful. Also, it goes worth saying that the complexity of this language of dependent type theory has an advantage of that modeling things becomes really easy. You can just think of what you want to model and specify it relatively easily, as opposed to these lower level tools where you have to really think of how do you encode it in that low level language. So those were some thoughts on the fourth level, which is really what this internship was. It was exploring this fourth category. I think in the future, we'd want to look at this third column here, because the rate of progress that we could make would be much faster if we don't have to design our own proofs. And there would be definitely some challenges in how we connect low-level code verification to high-level models. But F star, I think, would be a good candidate for this, whereas Daphne would be good for verifying code itself, and Alloy good for just models that don't include implementations. So lastly, one of the things that was focused on was verifying existing Soon code. But in the first slide, I had established that what I think the real value is developing new code using these techniques. So this also remains an avenue for future work. With that, thank you. Happy to take any questions, and note that a lot of the work here was made public, and you can find it on GitHub and Google Soon verification. So thank you.